Thanks for joining me. I'm Warren Baird, a product manager for SimForm, and I'm going to show you a quick demo of SimForm and how it can very easily help you understand the thermal behavior of your mold and your cooling channels. So first off, note that I am operating just inside a standard browser here. The SimForm is fully web-based, cloud-based. No computation happens locally. Everything happens in the cloud. I'm running on a very lightweight ThinkPad laptop here. You can operate on a phone or even a tablet if you want. So we're going to start off with what we call a channel planner, where you just have the plastic design in place. So we have a job here for the channel planner, and we have just the plastic part loaded. We happen to have the runners in here as well, which we don't particularly need at the moment, so I'm going to go in and hide those. Since we don't have a mold designed yet, we're going to make use of something we call the basic mold block. So when we turn that on, we will just create a default mold around your part. You can define the sizes. We kind of pick a default for you. And then you can pick the material that you want. In this case, we'll go P20 mold steel. And then the only other thing you need to tell us is you do need to tell us which parts are the plastic, because there may be additional things like the runner I showed you. And you need to tell us what material to use. So in this case, we're going to use polypropylene. We have the ability to add custom materials if you like. We have a few out-of-the-box ones, and you can add your own. And then that's it. You can go off and submit the job. So this then basically takes all of this information, pushes it into our cloud solver, and does the thermal analysis there. It's pretty quick, takes a few minutes to run, but to keep the flow of the demo going, I'm going to actually do a bit of a cooking show demo and switch to a pre-baked version that I ran earlier, just to show you kind of what the results will be like once that finishes. So in terms of the thermal analysis, we do like a full temperature analysis of the mold, and then we also do what we call a freeze time analysis. So we take a look at the outer 20% of the wall thickness, so 20% on either side, 40% in total, and we want that to be fully safe to eject. So we actually will go through and identify, based on the safe ejection temperature of the plastic, how long it takes each area on the surface of the part to reach that. And so we give you the overall time, which is the time for basically all of the outer shell of the plastic to reach that temperature. But we also show you visually which areas are safe to eject sooner and which areas are safe to eject later. Now again, the absolute time is when you're doing a channel planner results like this, is not necessarily super meaningful because you don't have proper cooling channels in place. But it still does give you an idea of which areas are going to accumulate the most heat, where you're likely to need to have cooling channels to help control the temperature. Again, and this is a relatively simple part, so it's not too surprising that the inner part of the shell and these areas around the ribs are kind of where you're going to need cooling the most. So the next step is to design your initial cooling channels. So I'm going to go in here and we'll create a conventional cooling design, and we can keep the plastic file in place, but I'm going to go back in and add some additional CAD files for the cavity cooling, the core, and the core cooling. And so now these additional files are going to be uploaded to our cloud solver, and they're going to be processed, and then they're going to be shown here so that we can see what they look like. It just takes a moment for it to basically process those files, and you can see all of the results here. So now we can go in and we do have to categorize the parts so that we know how to deal with them. So we can basically say, okay, well, I want this to be part of the first mold group, and I want that to be P20 like we did before, and then we can add other parts. So we can add the sprue bushing and these pins here. We'll add those in to the same category. I will add the runner in and categorize it as a runner. We treat those slightly differently when it comes to cooling. We don't require the runner to be as cool as the plastic before we consider the part frozen. And then I'll add the second chunk of the mold here, and I'll select P20 for it as well, and then I'll hide that, and then I'll also add the ejection pins into that group. Now the only thing left to do is we do need to know where the cooling channels are. So you can see now we've got the cooling channels here, And so we can basically select the cooling channels and we can add them in as channels here. So I'll add that one. We do need to know where the inlets and outlets are, or sorry, where the baffles are. But we have an automatic detection of baffles. So you can see these have changed to a different color because we've detected those as baffles. And so we'll do the same for this other channel. If the automatic detection doesn't work, we do have a mechanism to manually tag them. But in most cases, it does a pretty good job of identifying your baffles. And then the other two up here, we'll just we'll add as well. And then, as I said earlier, we do need the inlets and outlets as well. So we have an inlet-outlet selection mode. When you're in that mode, you can simply click and shift-click to select the various inlets and outlets. So it's pretty quick to just run through and add the inlets and outlets. And that's it. That's all you need to define for the simulation. So we'll go off and we'll submit the job. You can see the channel planner is actually progressing as we did that. But again, to kind of save a little bit of time, I am going to do the cooking show demo again and switch to the pre-baked version that I solved earlier. And you can see that that even before we look at the results, you can see that we're estimating 9 seconds. So that shows the effect that the cooling channels we defined on the freeze time. And so now you can see the freeze time distribution looks quite a bit different than before. You can actually see that it's cooling much more quickly on the inner part of the shell. We can actually overlay the channels, and so you can see that the tips of the baffles are indeed cooling the areas near the baffles pretty well. But you can also see that this area at the top here is not being cooled very well. The ribs are introducing quite a bit of heat in this area and making it harder for the heat to escape, and the baffles aren't really close to that area. We can actually go in and click on various areas if you want to see like precise values of various things. We can also switch and show a plastic surface temperatures. As I said, we do the full temperature analysis as well. So if you want to see the temperature instead of the freeze time, you can do that. You can, same thing, you can probe the temperature at various places. So you can see that it's up to around into the 85 to 90 degree range around those ribs at the front, and cooler throughout the rest of the body. And so at that point you can kind of make the call, well, do we think that this is both uniform enough and fast enough for our purposes? If so, maybe the baffles with a conventional design is good enough. But you might want to decide, okay, well, maybe we can do better. You know, what if we tried a conformal channel, see if that can help control, if we can get some cooling in around these areas here. So let's go in and we'll add a conformal design. And what I'm going to do is I'm going to remove the core cooling that we have here, and I'm going to add in a new file that has the conformal channels. So we'll add that file in, and so again, it's going to keep all of the other files in place, and it's just going to add the new cooling channels in place. Which is convenient, one, because it's less data to transfer back and forth, but two, it makes it easier to remember all of the settings. So you can see here that it's remembered what I had categorized as mold group 1 and mold group 2. So it still has the mold categorizations that we had before in the cooling channel and the plastic categorizations. The only thing that's different is you can see now we have the conformal channels, and those aren't categorized. So I need to go through the same steps I did before. I need to take those and flag them as channels, and I need to go into inlet and outlet selection mode and tag the inlets and outlets appropriately. And that's it. So now I can actually try the conformal run. Now you can see the conventional run is now underway as well. So it's not quite catching up to me, but it's pretty close. So the same thing. I'm going to go in and load the cooking show demo of the conformal model. And so yeah, So we'll go in and take a look at the results, although you can see the punchline here. So we dropped the time from over 9 seconds to about 6 seconds by adding those conformal channels in place. And so yeah, so looking at the design now, you can see that most of the inner part is actually cooling very, very quickly now. You can see down in these corners here and inside where these standoffs are, it's taking a little longer. Now, if you want to more directly compare the two views, we actually have a compare mode. So we can actually tell it that I want to compare the results of a different job. So I can actually take the conventional results in and compare them directly to the conformal results. So what we do is we actually load up both result sets and look at them side by side. And so you can see that you can rotate and zoom in and basically do all of the operations you can do in a single file, but we're now showing them on both models. And we can actually overlay the channels like we did before, and see the channels on top of each view as well. One of the things that we do here that helps is we actually use a single color bar for both views. So you can actually directly compare the colors on both of them. And so you do see areas here. This dark red means that it's off the top of the scale bar. So you can see these are the areas where this took longer than 6.6 seconds to freeze. And so yeah, so this gives a really great way of understanding how different cooling channel designs are going to impact your results. It lets you very quickly and easily, as you can see, it didn't take very long at all to set these up and run them. You can very quickly and easily do an analysis and get an idea of what the cooling behavior is going to be like, where your hot spots are, where your cool spots are. Sometimes I've seen cooling channel designs that have, they just add cooling channels every 2 inches or something, and so you end up with areas that are naturally going to be relatively cool that still have cooling channels next to them, which is kind of a waste of effort to have cooling channels in places where you don't really need them. And it helps you make the call about whether more advanced techniques like inserts or conformal channels are actually going to buy enough of a benefit to justify the additional cost and time of doing these things. We can also show, for instance, a cutting plane. So if you want to see what things look like in hidden areas, we can actually take a cut plane and we can move it around so that it sits where those standoffs were. If you want to see the behavior around the standoffs, that's relatively easy to arrange. We can just drop a cut plane through them. And that lets you see what we showed before, where even in the conformal view, these standoffs are actually the last thing to freeze. So if you decided that 6 seconds isn't enough, you could actually go ahead and add inserts in these areas and see if that you can trim a few more seconds off of the time. And so that's it for the demo. Thanks for your time. I hope this helped you understand how easy it is to do a thermal analysis of a mold and your cooling channels with SimForm. Feel free to contact us if you have any questions, or sign up for a free trial at simform.app. Thank you.